Okay, the next lesson, 7.2, is on two theorems called the no-choice theorem and angle-angle side theorems. We're going to go back to proof just for this one section here. If you look at the targets, it says I can prove the no-choice theorem and I can prove the angle-angle side triangle congruence. So notice those are theorems that we're going to be using, and that's the third target that I can apply these theorems. But notice these specific targets that I can actually prove the theorems. We don't always do that, but we are in this lesson. So again, two theorems, one called the no choice, one called angle-angle side. I'm going to prove them, and I want you to be able to prove them, but then we're also going to use them in proofs, and I'll show you the difference. Okay, so the no choice theorem basically says this. Draw yourself two triangles. Let's label this one ABC and this one DEF. And the no choice theorem says that if you have one pair of angles that match and two pair of angles that match, then by the no choice theorem, the third set of angles must match. So it's not a triangle congruence, it just tells you that if you have two angles in one triangle that match two angles in another triangle, by no choice, the third angles have to match. So let's write it out this way. If two angles in a triangle are congruent to two angles in another triangle, then the third angles are congruent. I'm not going to make you write all that out when you want to say it. I'm going to let you just call that the no choice theorem. Okay. Biggest mistake though is students want to use this as a triangle congruence. So I'm going to put here not a triangle congruence. In other words, it's not side 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 or side angle side or angle side angle. Right? So you want to make a note. This is not proving triangles congruent. It's just getting these third angles congruent. If two match two, the thirds match the thirds. So let's actually jump right down here. I'm actually going to prove to you why this is true. And it uses some of the things we learned in the first section. So we're given that A matches D and that B matches E. Right? So we're given this kind of information here. That's what we're starting with. If two angles in one match two angles in another, can we prove this theorem that we then want to be able to use in proofs? All right, so we're going to use what we learned in the first section, which is that the three angles in a triangle add up to 180. So angle A plus angle B plus angle C is 180, and angle D plus angle E plus angle F is 180. And I'm just going to say angles in a triangle add to 180, or you can say something similar. Now I see I have the 180 in both, so I know I can use substitution and set those two equal. Angle A plus angle B plus angle C equals angle D plus angle E plus angle F. That's just substitution. Right, if this equals 180, I can substitute that in up there. But now look what you have above. A and D are the same. So if I subtract them from both sides, right, that should be fair because they're equal. But B and E are the same. So if I subtract them from both sides, that should be equal, which means I'm left with, by subtraction, angle C congruent to angle F. Okay, again, this is just proving the theorem. So I'm going to circle this and star this. We're not going to do this every time we need to use it, but I want you to see why we know this theorem is true. Okay, we'll use it in a minute. We have a new triangle congruence. You can probably guess by looking at the targets. It's called angle-angle side. And you'll see why in a minute we haven't used it up to this point. I'm sure you can kind of guess what it means, right? So if we have an angle and then another pair of angles congruent and then the side, notice the order is important. The side is not between the angles this time, but it's angle, angle, and then side, then the triangles are congruent. So we're going to add to it. We have side, 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 angle, side, angle, side, angle. We added in HLR, and now we're going to add in angle, angle, side. All right, so again, we're going to prove the theorem. We're going to prove that this is true. Okay? We're going to also use it eventually in proofs, but this time we're just proving the theorem. So look at what we're starting with. G and K, H and M, whoops, I'll use different marks, and J, H, and O, M. Okay, so I'm not going to say angle, angle, side because I'm trying to prove angle, angle, side. If you're trying to prove a theorem, you can't use the theorem itself to prove the same theorem. So I have to use old ideas to show that this works. All right, well, using what we learned above, the no choice theorem, if I have two angles in one that match two angles in another, by the no choice theorem, I should be able to say that angle J is congruent to angle O. So you see, I'm just going to say no choice. That gets me those third angles congruent. Then, right, not using angle, angle, side because I'm trying to prove that, but now when I look at these pictures, I know there's an old triangle congruence I can use. Hopefully you see it. It's side, angle, side to get these congruent. Or not side, angle, side. Hope you caught that. Angle, side, angle. Angle, side, angle. All right. So angle, angle, side is really a theorem that can be proved using both the no choice and angle, side, angle theorems. But now we're going to be able to use it as a theorem itself and just say angle, angle, side. So again, remember, we were proving the theorems. That was those first two learning targets here. I can prove the no choice theorem and I can prove the angle, angle, side theorem. Now we're going to work on this one, which is going to be the bulk of your problems. We're going to actually apply them in proofs. So if you turn the page, I've got 3 examples for you. This first one is actually the hardest one. Let's mark everything up first and then we'll talk about what we're trying to prove. Angle N and angle R. Angle NTR congruent to angle P. NTR, that's this whole angle, congruent to angle P. And then I have a bunch of perpendiculars. I have TO perpendicular to NP. I have TS perpendicular to PR. And I'm going to squeeze up here TO congruent to TS. TO congruent to TS. All right, this one's a little tough because I'm asking you to prove a rhombus. So let's talk about what that means first if we dig back to chapter 5. To prove a rhombus, if you remember, a rhombus is part of the parallelogram family. So first you have to show or prove it is a parallelogram. That's the family it's in. There are 5 ways to prove a parallelogram, which you should remember from the last chapter. Opposite sides parallel, both of them, both pairs of opposite sides congruent, both pairs of opposite angles congruent, one pair of opposite sides congruent and parallel, or the diagonals bisect each other. So that's first on our list. Then to get from parallelogram to rhombus, we have to show that all the sides are congruent. All right, but technically we don't really have to show that all the sides are congruent because we know in a parallelogram opposite sides are congruent. So if we can just show that a pair of consecutive sides is congruent, that'll be enough to guarantee that all of them are congruent. So I'm going to say I have to show that consecutive sides are congruent. And if I have those 2 things, I can then say it is a rhombus. Okay? All right, so let's work on this one. Let's see what we have. I'm looking at these 2 triangles here and I think, well, I have an angle and I have another side. So if I could get another part, I might be able to get these triangles congruent. So I have perpendiculars. That would get me a right angle and a right angle. Let's start there. So angle ton and angle TSR are right angles. If perpendicular, then they form right angles. And then I'm going to go ahead and get them congruent because I don't think I'm using HLR. So I'm going to say if right angles, then congruent. And then I think I have angle, angle, side. Angle, angle, side. So notice I'm not proving the theorem this time, I'm just using it. So now I can say triangle ton is congruent to triangle TSR by my new theorem, angle, angle, side. All right, so now how do I use all of this information to show first that it's a parallelogram and second that consecutive sides are congruent? Well, first that it's a parallelogram, I'm looking at this pair of angles and this pair of angles, so I think I have that. I can say NPRT is a parallelogram because if both pair of opposite angles are congruent, then you have a parallelogram, right? So that's that check on the first one. Now I need to show consecutive sides congruent. Well, I have these triangles congruent. So I think by corresponding parts, these are consecutive sides, TR and TN. So I can show that TR congruent to TN. If triangles congruent, then corresponding parts are congruent. And that is enough to say NPRT is a rhombus, because if a parallelogram has consecutive sides congruent, then it is a rhombus. Okay? So I wouldn't ask you to do a proof like that without telling you how to prove a rhombus, but that's the idea. All right, so let's look at the second one. Second one here gives us some parallel lines, two pairs, AC parallel to XY and AB parallel to CY, and then angle ZAC congruent to angle XAB. So let's mark that up. Angle ZAC congruent to XAB, that's up here. And then I have these parallel lines. So let's start with this guy. AC is parallel to XY. All right. So if I use those, and I'm looking for a transversal, I'm going to pick this one out first. And I'm going to say that looks like an F. So I think I could get those two angles congruent. So I think I could get angle ZCA congruent to angle Y, because if parallel, then corresponding angles are congruent. But then they give me another pair of parallel lines, so let's look at that pair. That's AB and CD. And now I'm going to look at another F, and when I look at that F, I think I can connect angle Y with this angle over here. So angle Y congruent to angle ABX. Again, in fact, I could have put that with the same reason, then corresponding angles are congruent. So you could have even left that all on the same line. All right, I've double tagged this angle. Hopefully you realize what happens when you double tag, or if you just look here, hopefully you can see the hooking up, right? ZCA matches Y, but Y matches ABX. So I should be able to get these two to match right here by transitive. I can get angle ZCA to be congruent to angle ABX by transitive. So if I put the mark there, now I want you to look at these triangles, at this guy and this guy. All right, and think about what we learned on the previous page. I have two angles in this triangle that match two angles in this triangle. So if two angles match two angles, we learned by the no choice theorem that the third angle should match. So that's how I'm applying that no choice theorem. I'm not proving it this time, I'm applying it. And that's what I was asked to prove, to get X congruent to Z. Notice these two triangles are not congruent. This pink one down here is much smaller than this pink one at the top. So it has nothing to do with triangles being congruent. It just means that if you have two angles that match, the third angles match. Okay, so I want to keep reinforcing that. This last one is actually the easiest one, so let's do this one real quick. We have angle K congruent to angle J. And we have MR congruent to NR. And I'm trying to get MK and NR. So I'll give you one little hint here. I'm going to highlight these triangles. I think you should go after those. There's something you need to see in the diagram. Hopefully you're looking right in the middle. What kind of angles are these? Angle KRM congruent to angle JRN because they are vertical angles. So if vertical angles, then congruent. Now I think your triangles are congruent by that new theorem. Look at what we have. Angle, angle, side. Angle, angle, side. So pay attention to the ordering. Make sure it matches what you want. So I'm applying that angle, angle, side theorem that we proved on the previous page. And then, of course, by corresponding parts, we have MK congruent to NJ. If triangle's congruent, then corresponding parts are congruent. And that's it. So that was lesson 7.2.